Third part of my talk is about the Minkowski-Hsiung's formula applying on Alexandrov-Fenchel inequalities in a ball. The Alexandrov-Fenchel inequalities is a class of inequalities in convex geometry. So if we have a convex bounded domain in the Euclidean space with C2 boundary, then the quermassintegrals are defined as follows. W0 is the volume of omega, and W1 is the area of the boundary, and in general, Wk is the integration, the boundary integration of the mean curvatures. So the Alexandrov-Fenchel inequality for these quermassintegrals says that the ratio Wk over Wl to some power. So this ratio is a scaling invariant, and this ratio attains its minimum or infimum at a ball. Okay, so so we can view, especially when k is 1 and L is 0, this is exactly the isoperimetric inequality. So the Alexandrov-Fenchel inequality can be viewed as higher order isoperimetric inequality, but for convex domains. Note that the highest order of the quermassintegral, Wn plus 1, is in fact a constant, because here the highest order is the Hn, which is the Gauss-Kronecker curvature. So by Gauss-Bonnet-Chen formula, you can see that the boundary integration of the Gauss-Kronecker curvature is a constant. Okay. Yeah, we talk about a proof of Alexandrov-Fenchel inequalities for quermassintegrals by the inverse curvature flow, which was found by Tongfei Guan and Junfang Li. We see this the flow is with speed, a hypersurface flow with speed hk minus 1 over hk. Yeah, there are several properties for this flow. So along this flow, we have the following monotonicity, that this quantity Wk plus 1 over Wk to this power is non-decreasing. And the flow is satisfied that it preserves the convexity, and it preserves the K convexity, and also it preserves the star-shapedness. Here, the K convexity means the elementary symmetric function up to order K is positive. Yeah, and the flow has long time existence, and also asymptotically convergence. Asymptotic behavior is clear, that it expands to an asymptotically round sphere if the initial hypersurface is K-convex and star-shaped. Yeah, this was a result of Gehard and Urbas in 90s. So by using these properties for this flow, you can show that so the Alexandrov-Fenchel inequality for quermassintegrals holds for K-convexity and star-shaped domains, not necessarily convex domains. And if you use a rescaled or normalized inverse curvature flow, that is, you modify the curvature speed by a minus support function, and then you see Wk is preserved and Wk plus 1 is non-decreasing. In fact, if you check the first variation for the Wk, you will get the curvature, the mean curvature hk, then times this speed, and by Minkowski-Hsiung's formula, this vanishes. And for Wk plus 1, the first variation gives you hk plus 1 times the same speed, and then by using Newton-Maclaurin inequality, you see this is less or equal to the integral of this hk minus hk plus 1 times the pot function, which is 0. Here we prove that we see that wk is preserved and wk plus 1 is non-decreasing. And the flow here is in fact equivalent to the unnormalized flow in Euclidean space. Yeah, that means this flow and this flow are equivalent up to rescaling. Yeah. But in general ambient space, other than the Euclidean space, generally the normalized one is not the same as this non-scaled one. Okay. And the isoperimetric or partition problem in a ball is well known. So if you have a ball and you want to find the area minimizing hypersurface among all hypersurface inside this ball, which divides the ball into two domains, omega 1 and omega 2, with a given ratio of the volume of omega 1 and omega 2. Then the solutions are given as the all free boundary spherical caps or N balls, that is N geodesic balls. The solution was found by Burago, Matsuya, and Bolkowski and Spencer later. Okay. Yeah, they used the spherical symmetricalization method. And as we see before, yeah, we choose that the local minimizers to this partition problem in a ball are also all free boundary spherical caps or N balls. Now we want to study the Alexandrov-Fenchel inequality for quermass integral in a ball. So the first question is, what should be the right notion for quermass integral? So we restrict our consideration to the family of convex free boundary hypersurface. An observation of Lambert-Scheuer by using a result of Duchamp and Werder says that convex free boundary hypersurfaces must lie in a half ball. Okay. So we check the simplest one. So for example, if you have a curve sigma lying in a two disk, that is the one-dimensional case. Then from the Gauss-Bonnet, you see that the curvature integral of on sigma plus the curvature integral of t. That because t is a curve on the circle, so the curvature is 1. So then here you just plus the length of t, and these two you get pi. Okay, and in three balls, and you have a two-dimensional surface sigma, and you have the boundary of sigma lying on the two sphere. Then from the Gauss-Bonnet for this two surface with boundary, you see that the Gauss curvature integral over sigma plus the boundary geodesic curvature integration will be 2 pi. But here, because the free boundary condition, you see that geodesic curvature of a free boundary surface is exactly 1. So here this one reduced to the length of the boundary of sigma. Okay. So that means the highest order of quermass integral should be looks like this, or this one in one-dimensional case and this one in two-dimensional case. So what should be the highest order quermass integral in n dimension? So we found the following notion of quermass integral. So if you have a hypersurface in n+1 balls, dimensional balls, which is a smooth embedded free boundary convex hypersurface inside the ball, we define WK for this omega as follows. So omega is the enclosed domain of sigma with T. Okay, T is the part on the unit sphere. So here is the picture. Let me see. Yeah, this is the picture. So here is the omega. Okay, here you have sigma, you have T. Okay, right. Yeah, so the W0 is defined to be the volume of omega, and the W1 of omega is defined to be the surface area of sigma. Okay, and WK omega is defined to be the hypersurface integration on sigma of the mean curvatures plus some quermass integral, the spherical quermass integral of T. Yeah. So here, because T is a convex domain lying on the n sphere. So here there is a well-defined quermass. Here the W k minus 2T is the spherical quermass integral. Okay. It is the following first variational formula which motivates our definition of WK. We prove that if you have a family of smooth embedded free boundary hypersurface in a ball, given by the embedding xt from M to the ball, so which evolves by the flow with speed f, then there holds the first variation of Wk is given by the integration of hk times f, and the first variation of Wn plus 1 is 0. Okay, so from the last one, we can easily see that Wn plus 1 should be a constant. Okay. Yeah, this is the first variational formula for this quermass integral. So now we can show that in fact the Wk plus 1 is a constant which is given by omega n over 2. And by the definition, you can write down exactly what is the Wn plus 1. So the first dominant term is the integration over sigma of the Gauss-Kronecker curvature. Then you have the spherical quermass integral, which is given by a sequence here. Okay, so this is when the n is even, and when n is odd, still Wn plus 1 is a constant. And here the formula is a little bit different. In the first one, so in the even case, you have the last term is the boundary of sigma, the area of boundary of sigma, and in the odd case, the last term is the volume of T, or the area of T. Okay. Yeah. Then we show the following Alexandrov-Fenchel inequalities. So we still consider sigma as convex free boundary hypersurface in a ball, and then we see that the Wn is larger or equal to some function acting on its Wk. So here Fk is defined to be a variable function given by Wk of the spherical cap Cr. Okay, and here Cr is the spherical cap. That is what we have seen before. Okay, so the monotonicity of Fk follows from the first variation, and so that this Fk inverse exists. Okay, and notice that we only succeed to prove this Alexandrov-Fenchel inequality for Wk and Wn and Wk. So we want to get all result, that is, for any Wk and Wl, you have such kind of Alexandrov-Fenchel inequality. But we only succeed for Wn and Wk. The proof, so here is a corollary. So if you have 3 balls and the 2-dimensional surface in 3 balls, which is convex and free boundary, then this inequality, you can write it down as the integration, the mean curvature integration plus the length of t, the area of t can be larger or equal to some function times the area of sigma. And the equality holds if and only if sigma is a spherical cap or a flat ball. Okay. Yeah. Our proof is using the local quantity preserving flow. It's so it seems the speed is very complicated, but it involves here the conformal Killing vector field Xe here. So we assume the flow is the boundary condition for the flow is that the boundary is free boundary. Okay, the boundary of sigma t is perpendicular to the sphere, and we can prove the monotonicity, that Wn is preserved and Wk is increasing along the flow by our Minkowski-Hsiung formula. Okay. So this flow exists for all time and converges to some spherical cap, and this is the main analytic result we need to prove for this flow. Yeah. So here is the result for the flow. So the flow after the flow converges to some final one, x infinity, where this s infinity gives spherical caps. Okay. Yeah, about curvature flow with free boundary, there are a few previous results. So, for example, I list here a few by star for mean curvature flow, and convex free boundary hypersurface will shrink in finite time to a point along the mean curvature flow. When in a ball, it will shrink to an asymptotically half sphere. And this result was generalized recently by Hirsch and Martin in this year. So they proved that the sufficient convex free boundary hypersurface in convex domains should shrink in finite time to a round point along the mean curvature. And for the inverse mean curvature flow, still there are some results by Marquardt and Lambert-Scheuer. And for local quantity preserving flow, so we have some result for some special flows. So the sketch of the proof for the convergence of the flow. So the first, because this is local quantity preserving, so we can easily get a barrier for this along this flow. So this gives us a C0 estimate. That is because the spherical caps satisfy that the flow speed is always 0. So this spherical cap will not evolve along this flow. So this can play the role of barrier. And if the initial data lying in annulus of the spherical caps, and then it will hold on along this flow. Okay, and then you can get the higher function estimate. Okay, and by Lambert-Schroeder's result for convex free boundary hypersurface, so you can see that this xe dot nu, in fact, it is positive along the flow. Yeah, that means we can all, in fact, this is what we talked in the second part, that the hypersurface is star-shaped in this case, okay, in this setting. So then we can reparametrize this flow from the hemisphere. Okay, we consider conformal diffeomorphism from the half space to the unit ball. This is the standard conformal diffeomorphism, and then you can get the f star of the Euclidean metric is conformal to the Euclidean metric by this conformal factor. So interesting thing is that this conformal diffeomorphism, when you push forward along the when you push forward this conformal Killing vector field, you get the position function, the position vector field on the half sphere. Sorry, the half space. So the star-shaped condition is just in when you play on the half space, it is just like the radial the position function, the position vector dot with the normal is positive, and then we can reparametrizing this this flow to be a scalar function, an equation for a scalar function rho. So here rho is like the radial function as follows, and here rho satisfy the Neumann condition along the boundary. Okay, yeah, this is the first step. Then we can use the proof for fully nonlinear curvature flows, and you need to prove the curvature speed is bounded. Then you get the convexity is preserved, and then you prove that the inner product of nu and e is bounded above by some minus constant. Then you get C1 estimate, and then you prove the mean curvature bound. Okay, so I just omit the details for this proof, and later by using the Montonissi formula, you can get the convergence. Okay. Yeah. So if we want to get the full Alexandrov-Fenchel inequality in the ball, that is for any WK and WL, we need to study the flow convergence for general HK over HK minus 1. However, we do not know the main difficulty here is that we do not know how to get the convexity preserving for this flow. Even for the Minkowski case, we do not know how to do it. So we can see that, in fact, the importance from is that we use the Minkowski-Hsiung's formula to design this flow so that this flow satisfies the monotonicity, that one quermass integral is preserved and the other quermass integral is increasing or non-decreasing. Okay. Yeah, this is why we design this flow. Yeah. And however, we do not know when k is not n, if it is hk over hk minus 1, whether this flow exists for all time and has nice asymptotic behavior. Okay. Yeah, let's finish my talk, and thank you for your attention.